Welcome to the deep dive. We're here to get straight to the heart of complex topics, and today we're tackling something absolutely fundamental in robotics. It's this core challenge. How does a robot, any robot really, take some kind of input, a command, and actually turn that into physical movement, into action? This is, the essence of robot control. And if you've worked in robotics at all, it's a bit of a wild west out there.
Yes.
So many different actuators, motors, hydraulics, you name it, and just as many ways to control them. For ages, this meant engineers were kind of stuck, right? Rewriting similar code over and over for each new robot, each new sensor.
Yeah, solving the same low-level problems again and again. It really eats up time you could be spending on, the cooler, higher-level stuff.
Exactly. It felt like reinventing the wheel, or maybe a part of the robot's brain, every single time.
Yeah.
And that is precisely the problem that ROS2 Control aims to solve. It's designed as this elegant, standardized framework. The idea is to bring some order, some reusability to this whole complex world of robot control. So our mission today is basically to unpack the key ideas behind ROS2 Control. We'll look at how it works, especially in simulation, to give you a real shortcut to understanding this pretty powerful system.
And it's important to understand why we need something like ROS2 control, even when we already have ROS topics for communication.
Right, because ROS is already pretty fast.
It is. ROS topics are great for general communication, like sending goals or getting sensor data across the system. But for that really tight loop between the control logic and the actual hardware commands, sometimes even the small delay in ROS topics can be, problematic. You need almost instantaneous communication for really precise, stable control.
Ah, okay. So ROS2 Control provides a more direct, faster path.
Exactly. It creates this much faster channel. That's one of the key reasons it's necessary, especially for high-performance robots where timing is critical. And, looking at ROS2 Control for the first time, it can seem maybe a bit complex. There's definitely a learning curve.
Yeah, I can see people thinking, why not just hack something together quickly?
Right. And maybe for a quick one-off prototype, that works. But the real power of ROS2 Control, the huge advantage, isn't necessarily about making that initial setup faster. It's an investment. It pays off massively down the road. Think about reusing code, upgrading parts of the system, making modifications. It becomes so much easier.
So it's about long-term maintainability and scalability, not just getting something working now.
Precisely. It frees you up from the low-level plumbing to focus on the actual robotics challenges.
Okay, that makes a lot of sense. So it's this big, comprehensive system. Where do we even start trying to understand it? What's the core?
Well, I think the best place to start is right at the center. It's a component called the controller manager.
The controller manager, okay.
You could think of it as the orchestrator, the conductor, maybe.
Yeah.
Its main job is to find all the different pieces of code, the hardware drivers, the controllers, and link them all together, make sure they can talk to each other efficiently at that high speed we mentioned.
The conductor of the robot orchestra? I like that. You mentioned it uses a plug-in system. What does that actually mean in practice? Why not just run separate programs?
Ah, good question. The plug-in system is key to its efficiency. See, these hardware interfaces and controllers, they aren't separate programs you launch one by one. Instead, they're libraries. The controller manager dynamically loads them right into its own process when it starts up.
Oh, okay. So they're running inside the controller manager.
Essentially, yes.
Yeah.
This allows for that really tight, fast integration we talked about, less communication overhead, better performance. And it simplifies things because the controller manager handles their lifecycle loading, unloading, starting, stopping.
Got it. That makes the efficiency aspect much clearer. But, okay, how does this system deal with the sheer variety of robot hardware? That's always seemed like the biggest headache. Two robots might look similar, but one uses serial for its motors, another uses CAN bus, or one lets you control position, another only speed. How does ROS2 Control handle that chaos?
That is exactly the job of the hardware interface. Sometimes it's also called a hardware component.
Hardware interface.
Right. Think of it like a translator, a universal adapter maybe. This piece of code is specifically written to talk to your particular hardware. It knows the specific protocol, serial CAN, EtherCAT, whatever it is. But then, crucially, it hides that complexity. It exposes the hardware capabilities in a standard ROS2 control way.
So the rest of the system doesn't need to know the messy details.
Exactly. You, as the person running the controller, just interact with these standardized interfaces. And there are basically two main types of these interfaces that the hardware interface provides. You've got command interfaces and state interfaces.
Okay, command and state.
Command interfaces are, what you can command. Things you can tell the hardware to do. like
Okay.
setting a target velocity for a motor or a target position for a joint. State interfaces are things you can only read or monitor. They represent the current status of the hardware. Think sensor readings, the current position of a wheel from an encoder, its current velocity, maybe even the battery voltage. You can't command these, you just observe them.
So command is do this, state is what's happening.
Precisely. Let's take a simple mobile robot, like a two-wheel differential drive.
Okay.
You might have two command interfaces, both for velocity, one for the left motor, one to the right. And then maybe you have encoders measuring wheel rotation. So you could have four state interfaces: position for the left wheel, velocity for the left wheel, position for the right, and velocity for the right.
Got it. Two commands, four states in that example.
Right. And the really important thing here is, at this level, ROS2 control doesn't actually know it's a differential drive robot. It just sees, okay, I have two interfaces I can command with velocity, and four I can reposition and velocity from.
Ah, so it's completely abstract. It just sees resources.
Exactly. It's hardware agnostic at that interface level.
That's really clever. It explains how it can be so flexible. What if you have a more complex robot, say a mobile base with an arm on top? Each has its own motors and sensors.
They totally support it. A robot can definitely have multiple hardware interfaces active at the same time. Your mobile base might be one hardware interface, the arm could be another. ROS2 control handles this using something called the Resource Manager. Its job is basically to collect all the command and state interfaces from all the different hardware interfaces on your robot and put them into one big list that the controllers can then access.
Okay, so it aggregates everything. And how does ROS2 control even know these interfaces exist on a particular robot? Where is that defined?
It's defined in the robot's main description file, the URDF, the Unified Robot Description Format.
Ah, the XML file that describes the robot's structure.
Exactly. You add a special ROS2 control tag right inside your URDF, and within that tag, you describe the hardware interfaces, the joints they control, and the specific command and state interfaces available for each joint. It's like a manifest for the control system built right into the robot's blueprint.
Okay, so the URDF tells ROS2 control what hardware it can talk to. We have the hardware interfaces translating, the controller manager orchestrating. But how do we actually tell the robot what to do? Where does the high-level logic come in?
That's the role of the controllers. Controllers are the bridge. They connect the wider ROS world, your navigation stack, your manipulation planner, your teleop keyboard node, to the low-level ROS2 control hardware interfaces.
So they're the ones listening to things like CMD-vil.
Precisely. They subscribe to standard ROS topics, taking in commands like target velocities or joint positions. Then they use their internal algorithms, maybe a PID controller, maybe something more complex, to figure out the right low-level commands. And they send those commands directly to the hardware interfaces we just talked about.
Got it. So input from ROS, processing, output to the hardware interface.
Yes, but it's not always just a one-way street. Controllers can also publish information back out to ROS topics.
Oh, interesting. Like what?
Well, maybe feedback on how well it's tracking the command or publishing the current state that it's reading from the hardware interfaces. And here's a neat detail. A controller doesn't strictly have to control anything. Sometimes its main job is just to read state information and broadcast it.
How does that work? Why would you do that?
A classic example is the joint state broadcaster. Its whole purpose is to read the current position and velocity states from the hardware interfaces for all the joints and publish them onto the standard joint states ROS topic.
Ah, and joint states is what Robot State Publisher uses to figure out the robot's pose and visualize it in RVs.
Exactly. So the joint state broadcaster doesn't send any commands, but it's crucial for making sure the rest of the ROS system knows where the robot's parts actually are. It enables things like TF transforms for the wheels.
That's a really important function, even if it's not control in the typical sense.
Okay, so we have these controllers providing the logic. How do you tell the system which controllers to use and how to set them up?
That's usually done with YAML files. Simple text files where you configure everything.
Like ROS parameters.
Very similar, yeah. You create a YAML file and you pass it to the controller manager when it starts. This file tells it which controller plugins to load, what type they are, and any specific parameters they need. And once the controller manager is running, you can actually load, start, and stop these controllers dynamically using service calls or command line tools. It gives you a lot of flexibility.
So you could maybe switch between different control modes on the fly?
You could, yeah. Or just start the controllers you need for a specific task. It's also worth noting, you can often run multiple controllers at the same time on one robot.
Oh, really? How does that work without conflicts? The main rule is that different controllers can't try to claim the same command interface. You can't have two controllers trying to tell the same motor what velocity to use, right? That would be chaos.
Makes sense.
But they can safely share state interfaces.
Hmm.
Because reading state is passive, multiple controllers can simultaneously monitor the position of a joint, for example, without any problems.
Okay, that distinction is key. Command interfaces are exclusive. State interfaces can be shared.
Exactly. And this leads to another important point. Hardware interfaces are tied very closely to the robot's physical hardware, but controllers are more about the robot's application or task.
So you might reuse the same hardware interface code on different robots if they use the same motor controller, but you choose different controllers based on whether it's an ARM or a mobile base.
Precisely. And the good news is you don't always have to write controllers from scratch. The ROS2 controllers package provides a whole bunch of common pre-built controllers. Like there's the diff drive controller we mentioned for two-wheeled robots, controllers for robot arms, joint trajectory controller, grippers, lots of useful stuff ready to go.
That's great. Reusing well-tested code is always a win. Okay, so we've got the pieces. Controller manager, hardware interfaces, controllers. How do you actually run this whole thing? Get the controller manager started.
There are basically two main ways. You can run it as its own standalone ROS node. There's an executable for that, usually ROS2 control node.
Okay, just launch it like any other node.
Yep. The other common way, especially in simulation, is to have it embedded inside another process or plugin. The prime example is Gazebro's 2 control.
The Gazebo plugin.
Right. When you use that plugin, it actually starts up a controller manager instance inside the Gazebo simulation process itself. But either way, whether it's standalone or embedded, the controller manager needs two key pieces of information to start. Details about the hardware interfaces, which it usually gets by parsing the URDF, and the configuration for the controllers you want to use, which it typically gets from those YAML parameter files we talked about.
Got it. And once it's running, how do you interact with it? To load or start controllers, for example.
The main way is through ROS services. The controller manager exposes services to list controllers, load controllers, switch controllers, and so on. But calling services directly can be a bit tedious. So there's a really handy command line tool. ROS2 control?
ROS2 control, okay.
Yeah, it's a wrapper around those service calls and makes it much easier. You can just type ROS2 control list controllers, ROS2 control load controller, things like that.
Nice. That sounds much more user-friendly.
Definitely. And you also often use dedicated spawner nodes or scripts, especially in launch files, to automatically load and start your desired controllers when the system comes up.
Okay, that covers the architecture and how to run it. Let's make this more concrete. How would you actually set this up in practice, say, for a robot in Gazebo simulation? We don't need every code detail, but what are the main steps? I assume first you need to install the right packages.
Yep, that's step one. You typically need ROS-distro ROS2 control, ROS-distro ROS2 controllers, and ROS-distro Gazebo ROS2 control, replacing distro with your ROS2 version like Foxy or Humble.
Okay, core, controllers, Gazebo integration, got it. Then what? Modify the URDF.
Exactly. This is a key step. You need to add that ROS2 control tag to your robot's URDF file, often by including a separate .acro file just for the control setup. Inside this tag, you give your control system a name, say Gazebo system, and specify its type, usually just system.
And this is where you define the interfaces.
Yes. You specify the hardware interface plugin to use. For Gazebo, that's a Gazebo 2 control Gazebo system. This plugin is the magic piece that connects ROS2 control to the Gazebo physics engine. Then, crucially, you define joint tags for each joint you want to control, like left wheel joint, right wheel joint. For each joint, you list the interfaces it offers. So for a wheel, you might specify a command interface name velocity, and maybe state interface name position, and state interface name velocity.
So you're telling ROS2 control what you can command and what you can read for each joint in simulation.
Precisely. You're defining that abstract layer for this simulated robot. You also need to add the Gazebo plugin itself to your URDF, usually near the end. This is the libgazebros 2 control.so plugin.
And what does that plugin do?
It does a few things. It tells Gazebo to load the ROS2 control interface. It internally starts up that controller manager we discussed, and it automatically finds your robot's URDF, usually by looking for the robot description topic published by Robot State Publisher. And importantly, you also give this Gazebo plugin a parameter pointing to your controller configuration YAML file.
Okay. So the Gazebo plugin needs to know where to find the controller settings, which brings us to the next step. Creating that YAML file, right? Let's say mycontrollers.yaml.
So you create this YAML file. Inside, you'll have a section for the controller manager itself.
What goes in there?
Things like the update rate, how often the control loop should run, maybe 30 hertz or 50 hertz. And very important for simulation, use in time to true.
Right, so it uses Gazebo's clock.
Exactly. Then you define your actual controllers. Each gets its own namespace in the YAML. So for our differential drive robot, you might define diffcont. You specify its type, which would be diff drive controller, diff drive controller.
And then its specific parameters.
Right. Things like the names of the left and right wheel joints, left wheel names, right wheel names, the physical wheel separation and wheel radius, the base frame, usually base link, maybe a publish rate for odometry, and whether to expect stamped velocity commands.
Okay, all the details that specific controller needs.
And you'd also define the joint broad controller here. Its type is joint state broadcaster, joint state broadcaster. It usually doesn't need many parameters. Its main job is just to publish joint states.
Got it. So URDF updated, controller YAML created. You rebuild your package, launch the simulation. What next? How do you check it's working and activate the controllers?
Good question. Once Gazebo is running, you should see some output mentioning ROS2 control. You can then open a terminal and use that command line tool. Try ROS2 control list hardware interfaces. This should show you the velocity command interfaces and the position velocity state interfaces you defined in the URDF for your wheel joints. That confirms the hardware interface part is working.
Okay, that's a good sanity check. And then activate the controllers?
Then you use the spawner. You run something like ROS2 run controller manager spawner diffcont to load and start your differential drive controller. And then ROS2 run controller manager spawner joint broad for the joint state broadcaster.
So you spawn each controller you defined in the YAML. And at that point, the robot should be controllable via ROS2 control. But how do you get TeleUp working again? The topic name probably changed.
Exactly. Your old Gazebo plugin might have listened on CMDVEL. But the diff drive controller typically listens on a namespace topic, like diffcont CMD Vellenstamped or diffcont CMD Vellingbell.
Depends on the ustem pevel parameter you set.
Right. So when you launch your TeleOptuous keyboard node, you just need to add a remap rule. Something like ROS2 run TeleOptuous keyboard, TeleOptuous keyboard rosargs, remap CMDVEL, diffcont CMD Vellenstamped.
Simple enough, just point the TeleUp output to the controller's input topic.
Yep. And you should be driving your robot around a Gazebo using ROS2 control.
Cool. And the final step is usually automating this, right? So you don't have to manually run the spawners every time.
Absolutely. You'd add execute process or node actions to your main simulation launch file, launch.sim.launch.py or similar, that run those spawner commands automatically.
So the controllers load and start right alongside Gazebo and the rest of your nodes.
Exactly. Makes the whole process smooth.
Okay, fantastic. That really clarifies the practical steps for getting ROS2 control running in a simulation environment. So, zooming back out, we've taken quite a journey through ROS2 control. We've seen it's this really powerful, standardized way to handle robot control. It aims to make complex systems easier to manage, easier to adapt, and crucially lets you reuse code effectively, which ultimately, as you said, frees up engineers to focus on the bigger picture, on innovation, rather than the low-level control details every time.
Absolutely. And, what we've discussed today really is just scratching the surface. ROS2 control has a lot more depth for real-world complex applications.
Oh, yeah? Like what sort of things?
Well, there's functionality for controller chaining or cascade control. This lets you build more sophisticated control strategies where the output of one controller feeds into the input of another. Think like a high-level motion planner commanding a lower-level joint trajectory controller.
Hierarchical control. Okay.
Right. It also supports having different components updated at different rates, which would be important for efficiency. There's support for asynchronous execution for tasks that don't need super strict real-time guarantees. Plus, there are concepts like semantic components for more abstract definitions and a whole suite of tools for debugging and introspection, which are absolutely vital when things inevitably get complicated.
Wow. Okay. So it's clearly a very comprehensive framework built for serious robotics work.
Definitely. It's designed to be robust and scalable. And maybe just a final thought to leave you with. Think about this core idea in ROS2 control, these standardized command and state interfaces. It's not just about making one robot work better today. It's potentially about creating a common language for robot hardware interaction.
A common language?
What you know?
Well, imagine a future where you could take a robot arm from company A and easily integrate it onto a mobile base from company B, simply because both pieces of hardware expose their capabilities using these standard ROS2 control interfaces.
Like plug and play for major robot component.
Kind of, yeah. It could fundamentally change how we design, build, and integrate robots. It opens the door to unprecedented levels of modularity, reusability, and maybe even collaboration across wildly different hardware platforms. It's a really powerful vision for the future of robotics, enabled by this kind of standardization.